I wanted to finish off the example that I started in this morning's lecture. Of course, we're looking at surface integrals at the moment, okay? So what have we done so far? Well, we've motivated the subject. We've looked at parameterized surfaces, okay? Curvilinear coordinate system. We've looked at how to construct the area of a surface. And I finished the last lecture on defining surface integrals of scalar-valued functions. Okay, so just a quick reminder. Essentially, what we do is we parameterize a surface that sits in R cubed. Okay, you can think of this rectangle in this picture representing the domain of our parameterization. So in other words, that vector function phi is our parameterization, right? All right, so essentially what we want to do is calculate the surface area of this surface and also integrate over this surface. All right? And like I said in the previous lecture, a lot of these ideas are analogous to when we worked at integrating over curves, path integrals, line integrals. Okay, so anyway, I've talked about this, and throughout we make the following assumptions. Okay, we assume that the domain of our parameterization is an elementary region in the plane. The parameterization itself is nice and smooth and one-to-one, except possibly on the boundary of the parameter domain. And the surface itself is so-called regular. In other words, the cross product of the tangent vectors is non-zero, okay, except possibly at a finite number of points. All right, so the big theorem that we looked at in the last lecture was the following, okay? It told us how to calculate the surface area when we have a parameterization. Okay, we construct the tangent vectors, TU and TV, take the cross product and look at the magnitude of that cross product, and then we integrate over the domain D, okay? All right, so I justified all that last time, so I'm not going to go through it again. Now, our analysis on the surface area led us to define a new idea called the surface integral of f over curly s. Okay, this is how we denote it, and this is actually how we compute it. Right, now sometimes we use this normal vector to denote the cross product of the tangent vectors, but be warned, this vector here is not necessarily a unit vector, and the tangent vectors are not necessarily unit vectors either. So it differs a little bit when we were looking at, for example, flux in the plane and unit tangent vectors of line integrals. Yes?
So this formula here is similar to what we saw between the path integral transformed into a function.
Mais oui. Yes. Yes, it is.
Here the absolute value we take is of the cross product of the vectors instead of the derivation.
Yes, instead of the derivative of the parameterization. See, so for path integrals you would have a c dash there, right?
Yes,
c dash of t. Yep. So, yes, perfect.
and what is it going to become for triple integral?
Well, hang on. Well, I think probably a better question there is what do you think it will become for when we start integrating vector fields? Maybe here you'll have a dot product instead of just this scalar multiplication between the scalar function f and the magnitude. Oh. All right. So, in fact, in the previous lecture, you asked me, what is this good for? And I was delighted that you asked. One application of these surface integrals is calculating the mass and moments of thin shells, like bowls, metal drums, and domes, okay? In particular, if we have a given density function, then we can always calculate the mass of, for example, a shell. All right, I justified that, so I'm not going to look at that today. And then here are some more formulas. Now, of course, here you may think, what's this d sigma? Throughout here, d sigma is just ds. All right, it's just that Thomas's book uses d sigmas instead of ds's. Notice it's a capital S, by the way. All right, when we looked at path integrals, it was ds with a small s. It's a significant difference. A significant difference. Okay, similarly here as well. Then we talked about the integrals, surface integrals, over graphs. And this is actually the nicest case. All right? When we have our surface being a graph, in other words, we can write it in this form for some function g, then we can parameterize the surface in this natural way here. Okay? In that case, and it's quite easy to do this, you can calculate the tangent vectors and look at the magnitude, and you get this. Okay? And so, the actual surface integral can be written in this manner. Okay. So I finished the last lecture with the following problem. We were given a scalar valued function f. We were given a surface, which was the cap of this sphere for z greater than or equal to 2. And we were asked to integrate the given function over the cap of the sphere. All right? So let's just run back over that. First of all, we parameterized our cap. Now, the nice thing about this surface is that I can rearrange it and make it a function. Right? It's a graph. So the little cap that we're talking about is just here. Okay, so I've intersected the plane z equals 2 with the top part of the hemisphere, and I came up with this circle here. All right? So what does that do? It gives us our parameter domain for our parameterization, our surface. Basically, this disk is just, so this disk and this disk is the same. And that is the parameter domain for my parameterization. Okay? Okay, so I then wanted to try to apply this formula down here. So I calculated the partials of g, squared them, added them together, and I evaluated f at x, y, and g. So here are the partials, and here's this expression here. I evaluated f at x, y, and along g, and I came up with this. So what I do now is I put them all together. All right, so here it is. Okay, so I take these two things. Oh, I need to take the square root of everything here, so I might just add that in now. Okay? So multiplying these two things together, I want to take the integral of that. that expression. Okay, now we're going to get something a little like this. So that's going to go to a 3. All right. All right, so you can see now we're going to get some nice cancellation going on. So what are you going to get? We're going to get something like 2/3 times the root 9 minus x squared plus y squared. Okay, so now we've broken it down to a double integral that you should recognise or at least be comfortable with evaluating. Okay, you looked at this with the several variable calculus stuff. All right, so our D here is, of course, just this disk. Okay? Now, because it's a disk, you would think that it's reasonable to move to polar coordinates here. Right? Okay, so let's move to polar coordinates and see how we go. Now, if I move to polars, I'll get something like this. Okay? And that 9 minus x squared plus y squared is going to become 9 minus r squared. And what's the dA going to become? R d theta. Yar. Okay? So now it's quite simple. We can probably do this in one step now. The integrand doesn't involve theta, so we can just put a 2 pi expression down. Okay, so I've done the outside integral. And the inside integral is going to be something like this. What's going to be 1/3 or something like that? Minus 1/3. Right? Everyone agree with that? Yep. So now it's just a matter of cleaning up, putting in your different values for R. And after a little bit of work, and you substitute, okay, things are actually going to work out quite nicely here with this R squared. You get down to something like 3 cubed minus 2 cubed, but you should check the calculations. Okay. All right, so I've jumped a few steps here because I don't want to bore you with all the calculations, but you should definitely check that. All right. Now, as you can see, this was quite a long problem. Okay, it required a lot. First of all, it required to come up with a parameterization. And that's normal. In this case, the surface we were dealing with was a graph, so it was quite nice. Okay, it was easy to come up with the parameterization. It may not be so easy. You may have to switch, for example, to cylindrical coordinates. You may have to switch to spherical coordinates. But if you can rearrange the surface, the expression for the surface, so it's the expression for the surface, so it's a graph, my advice is to do it. Okay? All right, after that, we computed the partials here and basically applied the preceding theorem. Okay? All right, so that also involved evaluating a double integral. And in polars as well, All right, so it's a bit It's quite long, and, you know, but don't give up. You can do it. Sorry. Oh, cut. How can I simplify things even more? Is it possible? Well, yes, it is. Yes, it is. If our surface is a graph, okay, then there is another option here for basically computing our surface integral. Okay, and it involves the angle between the unit vector k and the normal to the surface. All right? So what do I mean when I say that? Well, I'll give you a look. Consider the following. Okay, here's our surface, and here's the domain. Well, basically, in this case, it's just the projection of the surface onto the xy plane. All right? Now, in this picture, here's the unit vector k. Here is a normal vector to the curve. It doesn't necessarily have to be a unit vector. Any vector will do here. And the angle between these two vectors is denoted by theta. All right, the claim is the following. You can compute the surface integral using this representation. Okay? So how do we prove that? Well, basically what we're going to do is go back to the previous theorem. Essentially, we're going to show that for a surface, z equals g of xy, this square root is 1 on cos theta, where theta is the angle between the k vector and the normal vector to the surface. Okay, that's all we're going to do. All right? Okay, so now there is a geometric way of explaining this too, which you may think is more obvious, but I'll leave that up to you, okay? All right. So, how can we produce a normal vector to a surface? Anyone remember? Yeah, even simpler than that. So you've got a surface. How do you produce a normal vector? Gradient, right? So that's pretty simple. So we produce a normal vector. Now it's not necessarily unit vector. To the surface, z equals g. Calculating. So we calculate the gradient of the vector field defined by z minus g. Okay? Now, you can, if you want to, calculate the normal vector by considering g minus z and taking the gradient of that. It'll still give you a normal vector, but it won't be an upward pointing vector. It'll be, so instead of looking like that, it'll look like that. All right, so in this case, it's going to be negative g sub x, negative g sub y, and 1. So you can see that this is upward pointing because the z, or the k component, is non-negative. Okay, if you had these reversed, you'd have a negative 1 here and positive signs here. Okay? So upward pointing is how we call this. All right. So I'm going to denote this by n. All right, so what about the magnitude of n? Well, the magnitude of this upward pointing normal vector is just starting to look familiar? Okay. Now, what else can we deduce involving the angle between these two vectors? Well, if we have two vectors here, we know that the dot product of these two vectors is just the magnitude of each vector times the cos of the angle between the vectors, right? Just the standard dot product. Okay, so if k is the vector 0, 0, 1, then the dot product of these two things is the following. Okay, now the length of the unit vector k is just 1, of course. Oh, okay, so the left-hand side is going to be the following. Okay, what have we got here? We've got... Okay, I'm going to abuse the notation here and put a k in. All right, should be a 0, 0, 1, really. Okay. So now all we need to do is work out the dot product on the left, which of course is 1, and rearrange to make cos theta the subject. Okay, so now we can go back to our earlier representation, yeah, and just replace it with 1 on cos theta. Okay? Oops, yep. All right, so where is this useful? Where are you likely to actually use this computational tool? Well, glad you asked. Let's have a look at that. All right. Here's a simple example. Now, there's a fast way of doing this and a bit of a tedious way of doing this kind of problem. All right. Now, let's see what we've got here. We're given some scalar field here, right? We're given a surface and the domain, parameter domain, right? So let's actually have a look at what's going on. If I sketch a cross-section of the surface that lies in the YZ plane I'm going to get something that looks like a line, right? Okay? Now, think of the x-axis coming out of the screen. Okay, so the x-axis is coming out that way. All right? You can think of this plane sitting in, of course, in 3 space, right? But the question is, can we easily get the angle between the k vector and the normal to this line or this surface? And the answer is, well, yes, we can. Right? The k vector is going to be looking something like that. Again, here I'm only sketching it in the yz plane, okay? But the principle is the same. And the normal vector is going to look something like that. Now, what do you expect the angle between the 2 vectors are going to be? Yeah, 45, right? Pi on 4, 45 degrees. So if that's my normal vector there, right, so a simple geometric argument can simplify these calculations greatly. All right, so let's use the previous theorem to work out this integral. Now notice here, the angle is fixed, no matter where on the surface you are. Okay, it's always pi on 4. So cos is fixed. And this is a good place to be if you want to use this formula. Okay. Other surfaces where you can use this type of computational tool are cones. Okay, cones are very good. Planes are good. But you'll get a feel for it the more questions you do. All right, so f at x, y, g is going to be, what's it going to be? X plus y, okay, because the y comes from there. All right. So essentially we're integrating the following. Now, you can see up here, this is our parameter domain. Now, by this notation, of course, I mean 0, 1 crossed with itself. Whoops. Okay. All right, so now it's just a simple double integration. We're going to get something like x squared plus 2xy. Okay, so if we sub in x equals 1, we're going to be integrating something like 1 plus 2y dy, and x equals 0. Okay. So, we get, 2 root 2. Right, so that was a lot less fuss than the previous example that I sort of spanned over 2 lectures. Okay, so use these computational devices to your advantage. Okay? Use these computational devices to your advantage. Now, in the next lecture, we'll look at integrating vector functions over surfaces, and in particular, looking at flux across surfaces. Okay, we looked a little bit at flux over closed curves. And I still think a few people are a little bit cloudy on the issue. Maybe I didn't explain it properly, but I hope to do a better job this time. Okay, so I'll see you all tomorrow.